Hey, I'm Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast will help you understand the chemistry of your everyday life.
Hey, Jam, what's up?
Not a lot. Just hanging.
Well, are you ready to hear about what you're going to learn today?
Yes, I'm ready.
I'm really excited about today's topic. And actually, it came from a listener. So I learned about this a long time ago and thought it was really cool and have not thought about it much since. But one of our listeners, Eris, reached out and asked a lot of questions. Some of them we'll circle back around to, but this one I thought, oh, this is such a good episode. So many people wonder about those science jargony words that are thrown out. So I thought that was a really good one. So thank you so much, Eris, for reaching out and even sharing about us. Okay, this one is very cool.
Okay.
It's about antioxidants.
Nice. I have no idea what those are.
Have you seen them like advertised for, rich in antioxidants?
Yeah. Or like, I think some sports drinks talk about it a lot too, because they're like, hey, you're playing sports. You want to have as many antioxidants as you can so you can do the sports.
Do the sports.
So it seems like it's related.
Yeah. So today we're going to talk about what is an antioxidant.
Okay.
What is a free radical?
Okay.
And then you're going to be able to tell me back all those things.
Okay.
We're going to talk about where you can find antioxidants and stuff too.
Okay.
I think this is really fun. When I learned this, my mind was blown.
Really?
Yeah.
Are you okay?
I'm okay.
Okay.
I survived a mind blowing.
Okay.
So just to dig in, do you remember what electrons are?
Yes.
You remember electrons?
Mm-hmm.
They make up an atom along with protons and neutrons.
Mm-hmm. They're in a cloud kind of thing.
Yeah, they call it a cloud. That cloud is really the area where they are likely to be present.
They're sort of a field. They're an aura. They're a mist.
They move around in that area.
A spirit. They're almost like a spirit. A ghost.
Yeah, well, and we've never seen them.
Oh, man. That's pretty crazy.
So in chemistry, electrons like to be paired. And I'm not going to get into why because that's kind of a spoiler for a later episode. But they like to be paired and things get a little sketchy when they're not paired.
Okay.
They become very unstable, kind of crazy. They want to react and find another electron quickly. Very reactive, very unstable when there's just one electron. Normally they move in pairs. When it's one electron by itself, it's called a radical, which I think is so funny because they're very radical. They're like trying to react.
Yeah.
They're being crazy. They're out there. They're going to cause problems wherever they can. They don't care as long as it gets them another electron.
Huh. Okay.
Like radicals. So I thought that that's a funny instance in which science almost personifies
Yeah. Oh, yeah, it does.
their
You're right.
behavior. Yeah. So radicals are well documented to contributing to aging, disease. They break down the ozone layer. They're not great.
Interesting. So they really do go crazy. It's not just that they're like moving around like crazy. They're causing problems when they're alone.
But
Got to watch the loners.
gotta watch for those loners. but I hope you know by now in chemistry, nothing is black and white. So nothing's all bad or all good.
Right.
Right? So actually radicals are also used for some really cool stuff like making polymers. They kill bacteria and they're even used in the treatment of some cancers.
Huh.
So they can do damage.
Yeah.
But they can also be constructive and do damage to bad things, which is good ultimately.
Yeah.
Nothing is all bad or all good in science, but radicals can contribute to bad things as well as good things.
And that's kind of a good rule for life in general. Like most things are not just all one thing.
Yeah.
So it makes sense that it applies in chemistry.
The longer I've been in science, the more I realize that there's a lot of gray.
Yeah.
Early on, things are real black and white, and you get taught it's this or it's that. But as you dig in deeper, there's a lot that we don't know.
Yeah.
Okay. So often those radicals appear in nature as part of oxygen.
Okay.
So that's radicals. Now, antioxidants are called antioxidants.
Okay.
Because what they do is trap radicals, which is naturally found often on oxygen, antioxidants.
Oxidant. Okay. Interesting.
Is that a nice, oh, I see moment, you know?
So here's a question. Why is it that radicals are like really common in oxygen? Is it just like it automatically has that amount of electrons to where there's a one as a solo?
I don't have that answer just off the top of my head. Normally the structure of oxygen O2 is drawn with 2 bonds between it.
Mm-hmm.
Sometimes I've seen it drawn where instead of having those 2 bonds, there's actually 1 bond and then a radical on each oxygen. So it actually occurs maybe as a diradical.
Oh, interesting.
A radical on each oxygen.
And there's tons of oxygen in the world. So even if it's some portion of the time, that means there's a lot of radicals out there just in the air. We're around oxygen all the time.
Mm-hmm.
So that would make sense that it's me the most common and why it'd be named antioxidants instead of just anti-radical or something.
Yeah.
I guess.
Mm-hmm. I think that's how it naturally came to be.
Okay.
I think it could be complicated to explain the answer to your question of why it appears as a diradical, but we're going to talk more later about how sometimes molecules have 2 different forms they can interchange between, sort of, and they exist as something sort of in the middle. So the radicals on oxygen are unusually stable.
Okay.
I think is the best way to put it. There's an interesting article about this in Chemical and Engineering News where actually a professor from UNT was cited. So, go
nice.
Mean Green.
Mean Green.
So, but I think it might be a little too complicated to honestly really get into and maybe not super helpful.
Okay.
So, now that's the basics of an antioxidant. An antioxidant is something that traps radicals and keeps them from moving around, banging around, causing all the damage they can cause in our bodies.
Does it give them an electron to be happy with? Is that how it does it?
No.
Whoa. I thought for sure it'd be like, hey fella, you're lonely. Here's a buddy for you. But it's not.
Well, that can happen.
Okay.
In radical reactions. Sometimes they use that where 2 radicals come together and then they're neutral.
Mm-hmm.
My OChem students who just took their final should all know about that.
And 2 radicals love each other very much.
But there's something else that antioxidants do.
Okay.
Okay, and this is a hard topic, but I'm going to explain it the best I can.
Okay, I'm in.
Are you a Marvel fan? Spoiler alert, we're about to talk about a somewhat recently released Marvel movie.
Yeah.
Great.
You've had a lot of time to see it, so
I actually haven't seen it, but this is the perfect
That's good though, because that means you can't really spoil the main stuff. You might be talking about something that's kind of ancillary to the main plot.
Okay, so in chemistry, sometimes molecules are drawn, and this contributes to why oxygen can exist as a diradical. Sometimes molecules are drawn as possibly having 2 different forms. Either these electrons could be bonded together or they could be off to the side.
Okay.
This double bond could be here or it could be here. So there's 2 sort of forms a molecule could take.
Okay.
A good representation of that is Bruce Banner and the Hulk.
Okay.
He can sort of take 2 different forms, right?
Yeah.
So molecules are drawn as having 2 different forms. But in the end, Bruce Banner and the Hulk come together to become Dr. Hulk.
Dr. Hulk.
Dr. Hulk is both Bruce Banner and the Hulk at once.
Yep.
In reality, molecules are not form A or form B. There's something in the middle where both of those forms contribute at once.
So is it really more like we observe it under, some sort of microscope or whatever it is, and we see it in a form, but it's not like it's always in that form all the time?
No. It's like Dr. Hulk. It is always both of the forms at once.
What? Mm-hmm. Oh, because we're just drawing them on paper trying to render how they're linked.
Yes.
But we're just trying to illustrate what elements make up a molecule, not really like putting in stone how they stick together.
Yes.
Got it. Okay.
Okay.
Yeah.
Science word, resonance.
I like that too because I'm like, okay, that resonates with me. Okay.
That what?
That resonates with me. All right.
No. So the best example of this that I've ever been able to find that is easily explainable is there is a ring that's made up of 6 carbons. So just imagine a hexagon.
Okay.
And every other side of the hexagon is drawn as having a double bond.
Okay.
So it's a hexagon. It's like 1 line, 2 lines, 1 line, 2 lines, 1 line, 2 lines, 6-membered ring.
Okay.
We draw it as a double bond alternating with a single bond. In real life, all 6 of those bonds are 1.5 bond lengths.
What?
Yeah. So if it really was, oh, this is a single bond and this is a double bond, this is a single bond, this is a double bond, it would be single bonds are, say, 2 lengths and double bond is 1 length or something.
Uh-huh.
Everything is 1.5 lengths. There's
crazy.
not actually those alternating things, but we can't draw that efficiently or effectively.
Right.
It's basically these electrons are shared all the way around rather than it existing in this solid form of every other one bond.
That's crazy. So, I mean, maybe I was told something like this at some point, but all that ever sunk into my brain when I was taking, chemistry in high school or whatever was just, here's how you draw these together. Here's where the bonds are. And it wasn't really I never thought about the difference between what this is on paper versus real life. Like, it just wasn't part of my thinking at all. But you draw those things where you have to get it right. Like, okay, how does it form together whenever these two things, like what's a water molecule look like? And you had to learn how to draw the lines the right way and remember the symbols and stuff. And that's as far as I ever got. It never occurred to me that it was going to be actually different in real life.
Well, what you're describing is a big barrier actually to science education. Students have a good understanding of what they're supposed to draw on paper or whatever, but they don't have a great ability to take that and understand that's a model. And this is a way of representing what's happening in real life.
Yeah.
And science experts have been exposed to so many models that they can look at that and have in their mind all of the models of that molecule. They know really, they have a better idea of what's happening in real life and not just on the paper. But novices, new students, they don't have that same understanding, and it's a barrier almost between the educator and the student.
Right.
So I'm so glad that you had that realization. Oh, so exciting.
And it seriously could be that I was told it and it just never sunk in, that I never got it. So I'm not trying to make any claim about not being taught the right way. I think it really is just the fact that I wasn't really trying to learn beyond what I just needed to pass a test or something. Right.
And that's hard. It's hard to motivate students to get that understanding or to communicate it. I had a great interaction with a professor at the University of Miami in Ohio named Dr. Brutz, and there's a very cool article about how she works to get students to actually understand what is going on in the molecule and not just on paper. So okay, so what antioxidants have is that sort of resonance. Usually they are long chains of alternating double bonds that can move back and forth is kind of the best way I can describe it, to actually give that all of them are more close to the 1.5 bond lengths. And when those encounter a radical, they will take that radical in and bring it into the resonance to where instead of the radical just being on its own, on an oxygen or whatever, it's distributed all along this chain of alternating double bonds, meaning the effect of that one radical is distributed by maybe, if it's 6 alternating double bonds or whatever, it's distributed and it's only felt 1/6 as much.
Oh, got it. So it's like they've got room to share this load. It's not like one person's trying to carry 2 backpacks. It's like 6 people, if you can imagine it, carrying 1.7 backpacks or something like that.
Okay, I think that's a good initial response. Just as a clarifying point, if one atom is carrying something really heavy, very reactive, that's like gonna be crazy, trying to deal with that one thing.
Like a lot of like acid or something, or that you,
I don't know.
Okay. Doesn't matter.
You've got one atom one person person being an atom holding something that like this is going to cause a lot of damage right now, and I can't get it to stop, then it brings in 6 other atoms to share the load, sort of. So then we're all working, all the atoms, all the people are working to calm this one thing down.
Pallbearers, kind of.
Pallbearers, yeah. And then the load is shared.
Okay.
And so instead of an insanely reactive radical that's going to bang around in your body doing damage to your DNA and making you look old and all these things, causing cancer, doing all this crazy stuff, instead it's just hanging out with a bunch of other atoms that can sort of disperse that crazy reactivity and chill it out quite a bit. So it's not one crazy Hulk. It's now Dr. Banner.
Nice.
What? It's now Dr. Hulk.
Yeah.
Yeah.
Dang, interesting. That's crazy. So our antioxidants is the structure you gave earlier of 6 carbons in like a hexagonal kind of shape. Is that the antioxidant molecule?
There's not one type of antioxidant molecule. So that is an option, but there are a lot of different ones. Usually what you'll see is alternating double bonds.
Okay.
They can be on a long chain. They can be in a ring. Alternating double bonds have that going on. Really, I think a better way to even describe alternating double bonds is you have a chain of carbons bonded and then a whole cloud of electrons around them. And a radical can just join in that cloud and it's not a big deal as much.
Got it.
So any alternating double bonds, that's going to be a good resonance thing going on. This is a hard concept to communicate. It's a hard concept for students to understand. Even if they can draw the right structures to represent resonance, sometimes they don't really know. Actually, this isn't exactly what it looks like in real life. It's really an average kind of. That's not something that is easily understood. So,
got it.
If you're feeling a little like this is kind of complicated, that's really normal. So don't get too worried about that. That's just the general. Alternating double bonds are usually going to have the ability to distribute the effects of the radical to make it more stable, and they'll be able to sort of diffuse the effects of the radical.
Okay. Interesting.
And that alternating double bond property does something else. It makes compounds very colorful.
Oh.
A molecule that has alternating double bonds, we'll talk about why in another episode, is usually going to be highly colored.
What?
So, if you have food that's red or blue or whatever, it probably has antioxidants in it.
Interesting. What?
Moral of the story, eat your blueberries and your tomatoes.
Yeah. That's weird. That's really weird. I have a lot of questions, but you already said we're going to do an episode.
We're going to do an episode on it. We cannot talk about colors and radicals and antioxidants all in one episode.
Well, that's so crazy because colors, those are pretty radical.
Oh, no.
Know what I'm saying?
Well, here's a little tidbit for you, a little science aha. Actually, colors are not radical because if a radical ends up interacting with a dyed fabric, it can disrupt those long chains of double bonds and remove the color from the dyed fabric. So,
bleach.
Have you ever washed your face with benzoyl peroxide? Benzoyl peroxide generates radicals to kill the bacteria on your face.
We're using the good in them.
And then you wipe your face with your mom's blue towel, and then it's pink, and she hates you forever.
Yeah. Even I have a blue towel. I don't even have to go as far as my mom's to.
And then it's bleached, and that's because radicals have disrupted the dye in that fabric.
Man, that's crazy. What the heck?
Isn't that? Have you always wondered why when you wash your face and then you dye those towels weird colors?
Well, I just always thought that, I thought it had some bleach-like property to it, in it. I didn't think about, molecularly. I just thought, okay, obviously we know that other things that clean stuff can also take color out, like bleach.
But I don't think bleach is radicals, and this is radicals.
Right,
so
right.
They're kind of different. So that's radicals, that's antioxidants, that's what is going on in all of that.
Okay, so
So next time you hear it on TV,
Yeah.
you know what those buzzwords are talking about. And you can just get them from Blueberries. You don't have to buy fancy water or whatever.
Do you remember that campaign that was like, Gatorade was like, Gatorade isn't in you? They could have just been like, radicals, are they in you? Here you go. We put some antioxidants in this.
Then they'll have to explain what radicals are.
Yeah.
That's not good marketing.
Yeah, it's really not. Yeah. Confusing your consumers. Really good start. Very, very good beginning.
I mean, that's what I do every week. So just kidding. I hope to clarify, not confuse.
So radicals are stray electrons.
Yeah.
They occur often in oxygen where there are just leftover electrons that aren't bonded together for some reason.
Mm-hmm. And other places.
In other places, not just oxygen. But that's why we get the ox part of the name.
Right.
So those can cause damage, and they can also be used for good things. But either way, they're just intense. Those stray electrons are all over the place. Whether they're doing good or bad, they don't care. They're going to do crazy stuff either way.
100%.
And so antioxidants are a category, I guess, of molecules that have
It almost is more a property that some molecules have.
a property that some molecules
Yeah,
have.
I wouldn't
Okay.
say like this is a category, antioxidants, whatever. It's like these are molecules that do these usually other things, but they also are nice because they can neutralize radicals.
Okay, so they have not one type of like structure, except that it does have to have that alternating double bonds thing you talked about, resonance, where it's got a not like perfectly evenly distributed bonds structure. Not everything gets one or everything gets two. It's constantly going back and forth. And because of that, because it's a team of molecules, at least a few. I mean, is there like a number? At least 3 or 4 like elements making up that molecule.
Well, it's usually a lot of elements making up the molecule.
Like
it's
6
just,
or
well, even
7.
it's usually there's all kinds of
Okay.
atoms and elements on everything, but it usually is a carbon chain
Okay.
of 6, even 4, but with alternating double bonds is
Okay.
really important. And there will be hydrogens around there and stuff too, but the alternating double bonds are usually demonstrated to appear on between the carbons.
Okay. So there's a lot of them, and they have that bond structure that's alternating, and so they can handle a radical in their midst because it's not like any one of them is bearing this crazy load.
Right.
They're able to kind of bring it into the group and have its craziness kind of shared across all of them,
Right.
and kept at bay.
Yes.
And so like, here, come hang out with us, you crazy idiot.
Yeah.
Um,
And then they chill it out.
yeah,
They chill the idiot out.
yeah.
That's a really good understanding. I do want to say one thing.
Okay.
You talked about how they go back and forth between the two forms.
Uh-huh.
It's drawn that way a lot of times to represent, but it actually is an average of the two forms. It's not one or the other. We don't ever catch, after he turns into Dr. Hulk, we don't ever catch Bruce Banner or Hulk.
Yeah.
There's always both of them present together.
Right.
That's
okay.
a good way to describe the resonance.
So it's
too.
always the average. Okay.
And the average is what shares.
And I do hope he stays Dr. Hulk. I don't know if we know what it's going to be like in the future, but
I don't either, but if he changes back, then that kind of messes with my whole analogy here.
well, the future is uncertain in more ways than one. Like, we don't know that chemistry won't decide to change on
Actually,
us at some point.
The chemistry won't change, but our understanding of it definitely could.
Right.
Definitely could. And I'm fine with that. I'm comfortable with that.
Yeah.
So that's it. You got it. That was a great understanding. And now next time you hear somebody talk about antioxidants, you know what they're talking about.
Yeah.
And they really are good. That's not one of those weird buzzwords that they put on things. Antioxidants are really good for you, but they're also naturally occurring in a lot of highly colored food. 2 of my favorites, blueberries, tomatoes.
Nice.
Very rich in antioxidants.
Interesting. It's crazy.
And if you want, we can put up a picture of some of the structure of those, but they will be the drawn representation and not the true average resonance.
That'd be sweet.
Okay, well, that's all for chemistry today. Do you want to share about something this week that brought you joy?
So something that brought me joy was, you kind of shared something like this, who knows, like 10 episodes ago or whatever, is that I'm not sick anymore. I was sick. It delayed our recording schedule.
Yeah. Oh my gosh, you were sick.
I had the flu. It feels so good not to be sick. So I'm just thankful. Like, it sounds like I'm complaining because it did suck hard to be sick. But once you're well again, it's like, oh man, it's so nice. It feels great. So I'm thankful for that. Brought me joy.
I'm thankful that you're healthy again too, because my life was significantly impacted.
Yeah.
Church on Sunday, I came to your house and literally shouted at you from across the house to greet you because I couldn't be in the same room as you.
Yeah, I had quarantined myself. Yeah. I'd recused myself from the...
from life.
Yeah.
One thing that really brought me joy this week is my students. I teach organic chemistry, which is not a fun class for many people, although it's my dream in life is to change that. And a few of my students had a really hard time and worked really hard, and they were in the end successful, and it was just really good to see that from them and to get to share in that joy with them. And now they're going to go into the break knowing that they were successful, and success looks different for so many people, but I just loved getting to be a part of their journey and demystifying some of organic chemistry for them. And there is nothing as rewarding to me as knowing that someone was intimidated by chemistry and then seeing the light bulb come on and the joy and the understanding. And it was just really nice to get to be a part of that. So I'm really thankful that I've got really good students this semester who are communicative, and it was just a really good end of the semester, and I really hope I get some of those same students again next semester.
Yeah. I think that's great.
Thanks, students. I know some of them listen to this show, so...
Bonus points, guys.
No, not actual bonus points, just bonus points in my heart.
Right. And in life, just, you're learning additionally. So...
Well, thank you guys so much for listening, and we want to take a chance to tell you that we hope you have a good holiday season. We know there's Christmas and Hanukkah going on right now, and even if there's not something that your family celebrates, a lot of stuff is closed around this time, and you get some breaks, and we just hope that everyone has a nice, restful season with the ones that they love.
Yep. Whether you're hanging with family or friends or whatever, or taking some time to yourself, hope it's an enjoyable time and a chance to rest a little bit.
That's right. Have a good, safe holiday. We did a poll about references on Instagram, and it was hysterical to me to watch the results come in because the scientists all said, keep those references in your show. Every single person who said to keep the references in the show was a scientist. And every person who said, take them out and put them only in the notes were non-scientists. It was so funny. I was really thoroughly entertained, but... because of that, and because our show is mostly aimed at people who don't already have a good understanding of science, we are going to change the way we do our references. They will always be in our show notes.
Yeah.
And if they're a major reference that I use a lot, I'll mention them as I talk about it, but we will no longer have a references section.
Yeah.
But I'm always really thankful to all those people whose work contributes to this show.
Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Instagram, Twitter, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, then you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jan Robinson. Jan Robinson is our producer, and we'd like to give a special thanks to A. Collini and In Newell, who reviewed this episode. If you'd like to help us keep our show going and contribute to the cost of hosting fees and other material, go to www.ko-fi.com/chemforyourlife. That's ko-fi.com/chemforyourlife and donate the cost of a cup of coffee.